I think we should start. So, welcome everybody to our seminar series. Today we have Dr. Tiago Bilo. He's an assistant scientist at CIMUS. So he received his PhD from the University of Miami in 2020, and then he spent a few years doing his postdoc, and then joining us last year, right?
Yes, exactly.
And he'll be speaking to us today about weakening of the aim of the solid in the North Atlantic. So, Dr. Tiago, so you have 40 minutes for your talk, and then after that, we're going to have 10, 15 minutes question and answer sessions.
Okay.
Okay, the floor is yours.
All right. Thank you. Hi, everyone. That's exciting. Like the return for the in-person talks, right? Fortunately, most of the people are still home because of our AC issues, but that's fine. I think that's the first step. The first step is always harder. So today I'm going to talk about the work I've been doing since October of last year when I started here on the weakening of the AMOC abyssal limb in the North Atlantic. This work has been under review in Nature Geoscience. I submitted 4 months ago, so I hope to have some good news soon. And yeah, let's go into it. So first things first, what I'm saying, what do I mean about the AMOC abyssal limb, right? And here essentially talking about the Antarctic bottom water flow that is mostly below 4,000 meters in the global oceans. And you've probably seen this picture before. I'm trying to use my mouse here. I hope you see my mouse icon going around. So in the Atlantic, it's essentially the flow that it's most of it's produced around the Weddell Sea by deep convection, and these very cold waters sink down to the abyss and flows northward towards the North Atlantic, below the North Atlantic deep water. So we're talking about this lower cell of the AMOC, right? And we know that the AMOC system is closely related to the variability in our climate system. So the million-dollar question becomes, is the climate variability that we're seeing around Antarctica, for example, is disrupting the AMOC at all? And if yes, how fast, right? So that's the main goal of most of the studies. And from observations, we know for a fact that the Antarctic bottom water has been changing, at least its properties and its production formation mechanisms has been changing and in the past 60 years or so due to climate change. So Antarctic bottom water has been progressively becoming less dense, and its formation has been decreasing during this time, right? So we want to know that did this type of processes had impacts on the rest of the global oceans. And when you think about it, most of the studies out there has been focused on what they're calling the shrinking of the Antarctic bottom water layer. So that's what we know from observations. So if you try to track the properties in the abyssal ocean, and that's globally, this is a figure from Horty and Johnson in 2010, one of the nicest figures I could find about it. If you track the ocean heat content, for example, in below 4,000 meters or so, since the 80s, most of the global oceans has been warming, all right? And that's everywhere, with except a few areas like the Eastern Atlantic Ocean, right here, and the Western Indian Ocean. But as a rule of thumb here, we find very consistent and robust warming. And that has been related to the shrinking of this cold Antarctic bottom water layer. And the hypothesis is that as we decrease the formation of the Antarctic bottom water, we weaken the lower limb of the AMOC, this abyssal limb of the AMOC, right? And we have this layer shrinking. And again, this is another another figure from Sarah Porky and Greg Johnson, where they quantified the volumetric change since the 80s of these Antarctic bottom water, right? Like at least using isotherms as vertical motions of the isotherms to quantify it. So if you track those changes along the main pathways of the Antarctic bottom water, such as the West Atlantic, East Indian Ocean, and the Pacific Ocean, we can verify that this cold layer, and now we're talking about everything that is a potential temperature below 2 degrees C here in this plot. Although Antarctic bottom water, depending where you are, especially in the South Atlantic, it's marked by the potential temperatures smaller than 0 degrees C. We have a negative or a contraction in the volume of those cold waters, all right? And this is an example. If you track the waters that are forming, for example, in the Weddell Sea and spreads northward along the Western Atlantic Ocean through the Argentinian Basin and then the Brazil Basin, we see a consistent contraction of those waters. But if you go a little bit north, and now you're talking about the North Atlantic, the signal is not quite obvious, right? So all the studies have touched this topic, and they all kind of show the same thing, is that we don't have a significant warming. In fact, we have a more strong indicator variability. So if you start looking at the variability in the North Atlantic, and this has been linked to the variability of the North Atlantic deep water, mostly, right? So this is kind of an open question, and one of the reasons as well that we chose the North Atlantic to explore. So I come back to this figure here, and we can ask ourselves, is the AMOC actually slowing down, or are we just seeing a generalized warming or changes of the properties of the Antarctic bottom? So there is still kind of like this connection is still quite not clear. Like we have changes going on in terms of seawater properties, but can we see that from the dynamic point of view, from the kinematic point of view of the AMOC slowing down or not in terms of velocity? So, and actually, numerical simulations suggest that that's exactly the case. All right. So essentially, if you perturb the formation of Antarctic bottom water, all right, around Antarctica in a model, so what's going to happen? It's going to trigger some wave response, topographic waves mostly, that can rapidly propagate this information northward in a few decades. So much shorter time scales than we expect about changes on advective time scales that can take hundreds to 1,000 years to cross the entire basin. So this information can get there really quick and enforce an adjustment of the flow, all right, and force a weakening of the AMOC, or weakening of the Antarctic bottom northward flow, I would say that. All right. So that's exactly what we investigate. We aim to investigate in this paper. So this is a map of near bottom potential temperature from the World Ocean Atlas climatology. So you can see the Antarctic bottom water as marked, mainly referred here as waters below 1.8 degrees C. So the bulk of this water crosses the Atlantic. Part of it can cross the Mid-Atlantic Ridge towards the eastern part of the basin. So the Mid-Atlantic Ridge is this masked area here in the middle of the basin, but most of it flows northward in the western part of the basin. All right. So as it flows north, and crosses enters the subtropic, it spreads and recirculates everywhere until it reaches latitudes around 30 to 40 north, where we have a lot of vertical mixing transformation, and this water can return and mixes with the North Atlantic deep water, and it can return southward. All right. So that's the general picture of the circulation, very simplified here. And the goals of our study was to infer the variability of the Antarctic bottom water flow in the subtropical North Atlantic. And for that, we use the MOVE array at 16 North that measured hydrographic properties at two locations, which are the little stars in the south here, between 2000 and 2020. And the gauge mooring arrays, which are current meter moorings that collected data in 2 years, the first 2 years of the MOVE array, across this transect here. And unfortunately, because we didn't have good coverage of this entire transect for several years, we had to relate this variability to the temperature variability further north, right? And for that, we use the hydrographic observations between 26 and 24 north from Wolf's and Goship, the historic A05 line, CTD line, right here, and the rapid and the Western Boundary Time Series from NOAA along this line here as well. So we use all the data that we can find out there around this area between 1998 and 2001, and we were looking to have a few deep Argo floats as well within this very tiny box in the middle of the Atlantic. All right. Not so lucky because the data were not that great, but the temperature and the pressure data was pretty much good in all profiles, so we were able to use that as well. Okay, so when I talk about when I talk about Antarctic bottom water variability or flow variability, I'm talking about geostrophic flow integrated across 16 North using the mover. All right, and this is done following 4 steps. All right, and here is just a transect of temperature from one of the CTD transects that we had, high resolution in CTD transects that we had. We had 2. So you can see the moorings shown by the stars. This is the colors are potential temperature, the 1.8 C degrees Celsius isotherm over here. So everything below this or colder than this is what we are considering Antarctic bottom water. So we calculate the geostrophic transport between those 2 modes, right? So it has microcats measuring temperature, conductivity, and pressure from the surface all the way to the bottom, which is around 5,000 meters. Okay, I'm going to get to why this 5,000 meters is important. So that's the first step, is to calculate the geostrophic shear between the MOVE hydrographic moorings. All right, this is pretty straightforward. Everyone has done that. That's pretty easy to do. Then things become a little bit trickier. So here we are using a level of no motion of 4,500 meters. And 4,500 meters is not a magic number. And you have to keep in mind that's a very critical step, because the sensitivity of the methodology is right here. Most of it, at least, is right here. All right. And we chose 4,500 meters for several reasons. All right. So first is the approximate depth of the 1.8 degrees C isotherm. So it kind of marks, let's say, the transition between North Atlantic deep water and Antarctic bottom water. Okay. This is true from the CTDs that we have and climatology. There have been out there numerical models as well. The other reason is that from numerical simulations that are being has been used to investigate this precise topic, they have all shown a level of no motion across 16 North of around 4,500 meters. All right, and here I'm talking about Gokhan work that has been published a couple of years ago. So from UCAR. So they have, his group has shown that 4,500 meters in terms of numerical simulations is also a good level of motion. All right, and here is the shallowest level that we cannot go further deep in terms of level of the most chosen of referencing level, and generate flows that we don't know about. All right. So essentially, if you use a deeper level and you do geostrophic calculation using, for example, a CTD transect like this, you're gonna see that if you choose around 5,000, for example, a lot of southward flow where we expect to see northward flow of the Antarctic bottom. So that's another reason that we chose this level of no motion. All right. And the third reason, and another reason, is that if you study velocity transects like this is from the gauge data, the current meter moorings, which are the gray stars, all right? We also see a level of no motion much shallow. That's around 4,300 meters, although there's a lot of caveats in this. And the third step that is also critical, but not too much, is the vertical extrapolation below 5,000, because the move moorings do not measure anything below that level. All right. So we have to use the velocity measurements from move and other sources of data to try to verify how impactful these extrapolation methods that we use. We used a couple of different things. I'll be happy to go through that after the talk, or if you're curious about. But we did a bunch of sensitivity tests, and most of them, all of them actually, show zero flow between 5,600 meters and 58, and this is mainly due to the shape of the basin. So below those depths, you can do lots of extrapolation exercise, and that's the uncertainty that we have. All right, and we incorporate that and propagate that uncertainty in our geostrophic transports as well. So everything in terms of uncertainty, this has been included in the calculation as well. And finally, we integrate the geostrophic velocities below 4,500 meters and call it that the Antarctic bottom water flow. All right. After all this, that's what we got. This is the mean in orange, the mean geostrophic velocity profile between the two moorings. So you can see 4,500 meters, we have positive velocities, which is the Antarctic bottom water flow, gets to the maximum, and below that, we have the extrapolation, that's the dashed lines. The colorful lines here are the calculations done the same way using the high-resolution CTDs that we have. And luckily enough, we didn't need to impose any extrapolation using those data, because they are high resolution in the horizontal. So we are covered that. It covers most all parts of the basin. So you can see that it's not perfect. It doesn't get the nuances of the flow below 5,000, but it generates a robust estimate. And our mean value of the transport is 2.4 icebergs, right? And that's the variability that we get. That's a time series, 18-month low-pass filter, so we can highlight the interannual to decade variable time scales. So that's the orange part, and you can see there's a clear trend overlaying that variability. In green, that's the linear model. This trend is about 0.02 isvardops per year. It's very small. And if you account for the reduction over a period of 20 years since 2000, we have around 12% reduction of the first year of data. All right. So that's the signal that we have. And as we see, there is a weakening of the Antarctic bottom water flow. All right. And why is that? So to try to answer that question, we need to look to the velocity again. So that's what we think is happening, all right? And we're going to show that is. So we hypothesize, all right, so what is driving that? We are using a level of no motion that is constant over time. So this variability that has to come from the geostrophic shear themselves, right? Or the density gradient between the east and west moorings. Simple as that. So what's going on is that if you look at this plot again, most of the Antarctic bottom water flow is against the mid-Atlantic ridge on the eastern side of the basin. You can see over here. So as this flow weakens, okay, and the layer contracts, this colder layer contracts, we have a flattening of the isopycnos and the isotherms between the western boundary current, or the western boundary, and the mid-Atlantic ridge. So that's what's going on, all right? And if you calculate in terms, so when we hypothesize said, all right, that story fits, right? And one thing that we need to do is then start looking at the variability of the properties of water that defines the density. So we did it in terms of temperature, salinity, and density, of course. And what we see that any changes in the geostrophic shear is actually driven by warming near the mid-Atlantic ridge, which is not happening. No warming, significant warming or trend is in the western boundary. So that's what it is. This so we calculated the trends, temperature trends. That's the green line, and you can see that below 4,500 meters, we have warming. All right. And this warming is mainly driven by the heaving of isopycnos. That's what the red line is showing here. So you decompose it, these trends in terms of heave, up and down of isopycnos, and spice component, which is temperature changes along isopycnos, right? And we see that the heaving of the isopycnos, that is driving the warming. And there's a quite strong heaving between below 4,000 meters or so, which is approximately almost the 1.8 C isotherm depth at the mooring site over the mid-Atlantic ridge. And when you put that on the calculation of the geostrophic shear, let's say, the signal pops up right away. So in green here, we have the geostrophic shear between the moorings, all right? 18-month low-pass filter, exactly the same way we did for the transport, for the previous plot. That's a green, all right? And we did a couple of experiments. So if you assume, for example, a constant density profile at the deep western boundary current, or in the eastern side, or the western side of the basin, doesn't let that vary, and use the original density profile that we get from the mooring over the mid-Atlantic ridge. That's the dashed orange line. And we recovered the trend in the shear and the transport just using the simple approximation, all right? And you can go even further. If you do the same thing, but now also fixing the salinity variability also in the mid-Atlantic ridge, just let the temperature varies. That's the magenta line. We recover the same trend, all right? There's the same trend. So the trend in the transport is being driven by the warming near the mid-Atlantic ridge, where we have most of the Antarctic bottom water flow. If you do the same thing now, but just but using a density, average density profile over the mid-Atlantic ridge, and let the deep western boundary current vary, we don't have the trend anymore. There's no trend, and actually we explain most of the interannual to decadal variability, but no significant trend. Meaning the trends, the long-term trends during those 20 years, it's associated with warming of the Antarctic bottom water layer near the mid-Atlantic ridge. Okay? All right. So we saw the weakening, right? And that's associated with the warming of the abyssal layer across 16 north. Now, we also wanted to see the general behavior of the layer, of the Antarctic bottom water layer. Unfortunately, we don't have enough CTDs or data or moorings covering the entire transect at 16. So we can study the entire behavior of up and down of the isopycnos or the isotherms at this latitude. So we had to move northward, all right? And that's where the data at 24 comes, 24, 26 north comes into play here. So that's the same potential temperature plot, but now for the northern transect, all right? Here is that's the section where we have 36 deep Argo floats. that we also use. When you look at this, you can see that most of the Antarctic bottom water layer, the bottom water layer is constrained to the east of 69 west, which is this, the transition here between the Western Boundary Time Series transect to the Wool's historical line. So most of the water is here in the deeper part of the basin, but there's an indication of some other water as well here. But we try to focus where we have most of the water, right? So we calculated the potential temperature trends across this section. And we used observations at the edge of this layer to study the variability a little bit further. But that's the focus of most of the results, all right? And that's what we got. Okay, so in this plot, again, we have in green the potential temperature trends as a function of that, all right? That's for the entire transect between the Mid-Atlantic Ridge and 69 West, all right? And in orange is for that smaller section where we have deep Argo floats. So we incorporate that in our calculation to verify the sensitivity to the amount of data that we have. So you can imagine when you start looking at hydrographic transatlantic transects, you don't expect many realizations of these transects, right? So we needed to include more data to verify the robustness of the calculation. So essentially, they're telling us the same thing in terms of Antarctic bottom water layer. So if you can see that both of them kind of have warming below 4,500 meters, all right? And this warming increases as we go downward in the water column. It reaches a peak of 5,500 meters, and kind of became steady and slightly decreases towards the bottom. And if you decompose those trends in terms of heave and spice again, the heave is the responsible mechanism for the warming. So that's because the isopycnol is going down, and this Antarctic bottom water layer shrinking, that we have the warming, and not changes along isopycnals, all right? But you can see that if you have spice, meaning we have cooling along isopycnals, here we have negative spice, right? It also means that we have freshening going on. So this layer is becoming warmer and fresher. Because if you're thinking about isopycnal surface, that doesn't change in terms of density. It's an isopycnal surface, right? So if you have warming to compensate, you need to have freshening to keep the density constant. Sorry, if you have cooling along isopycnal surface, you need to have freshening to compensate. That's the opposite. All right, yeah, there you go. So again, warming trend is constrained with the Antarctic bottom water layer. These trends are around 1 milli-degree Celsius per year. So you see that's very tiny, very small signals here, which is around half what you observe in the South Atlantic Ocean, or at least most of it. Near Antarctica can reach more than that, 5 milli-degrees C. And recently, Edmo Campos from University of São Paulo has been working in some of the records from the SAM project, some of the pies there. And one of the pies actually show whopping warming of 17 milli-degrees Celsius per year, which is very large. All right. So you can see there's some variability, some local process probably playing some role here. But the warming in the North Atlantic, in terms of basin-wide signal, is around half of what you find in the South Atlantic. Isopycnal heaving is the most important mechanism here due to forcing the warming again. And Then we did some experiments, trying to do some rough calculations on what are the impacts of this, all right? And if you think about it, this layer is below 4,000, 4,500 meters. It's still pretty large, right? You're talking about 2,000 meter depth layer, right? That spans the entire basin. So it's a quite large reservoir of water. So we started wondering, okay, if it's warming, like, and this has been shown by other studies in the South Atlantic and other places, do we see a contribution due to thermal expansion of this huge layer for sea level rise, for example? And what is the volumetric change of this water, of this layer? So we did some calculations using the moorings, using the isopycnal heights or the isothermal heights of this layer, and then we get some pretty consistent numbers, which varies between 1 and 2 times 10 to 14 meters cube reduction in 20 years, and that roughly is translated roughly in a contribution of almost 3 millimeters to sea level rise in 20 years. But those numbers, you have to see those numbers as rough estimates, because the uncertainties are so large and the signals are so tiny, right? We need to be careful in interpreting those. But the fact that we have some good corroboration between different independent calculations, and if you translate that to heat fluxes across 4,000 meters, 4,500 meters to the abyss, we also have consistent results with previous studies led by other authors. So we're quite confident that the uncertainty is still large, but we are in the right track in terms of, we think we are pretty confident what's coming. And to finish my talk here, those are the take-home messages that I want you guys to remember, right? The first one, the Antarctic bottom water flow at 16 north has decreased around 12% in approximately 20 years, all right? And we were only able to do so, to make this calculation, because we have 20 years. If you only had 10, if you only had 5 years, we would have a very different result due to the large interannual variability of this record. The second take-home message here is that the abyssal flow weakening is associated with the contraction of Antarctic bottom water layer, and consequently abyssal warming, right? Heaving of the isopycnal contraction of that layer is forcing the warming, where we have most of the Antarctic bottom water, and that is forcing the vertical geostrophic shear, and consequently the transport of Antarctic bottom water flow. All right, and it seems to have a contribution to sea level rise in the North Atlantic. I put an interrogation mark here due to the uncertainties, right? Remember, those are rough estimates. And the estimated warming rates, they are on average half of the observed trends in the South Atlantic that has been out there. So meaning that we could see a potential dilution of the signal as this water flows northward. So imagine that along its way, it's constantly mixing with North Atlantic deep water. We can expect that those signals get mixed in and interfere with each other. So as we go to North Atlantic, we have more North Atlantic deep water, and so a dilution of the signal. All right, and I'll finish my talk here. Please let me know if you have any questions.